Hello, and we're here with data science teacher Brandon, and we're going to go over the ARD regression in sklearn. It's the automatic relevant deterministic regression. And basically allows you to control the amount of regularization. Kind of helps it adapt to each column. So it, to me, is my favorite regression, linear regression. There's definitely better models, but it works really well as I use it as my baseline model for most of my test cases. It makes a lot more sense than linear regression because it actually has a good shot. Maybe not being the best model, but being above the top ranking models for so it's really good and it's still at its essence really simple linear regression. Yeah, I'm turning off some of the warnings here today, importing linear regression, ARD regression, and then importing test split and some other standard data sets. So we're going to do set colors and it's different colors mixed up a little bit, changing the color palette here, and then importing the possums data set here to, and we're going to predict the age. So this is definitely not a typical prediction, not really the intention of this data set, but to make it a really hard prediction, I wanted to see the effects of the model as we go through it, and we're going to iterate through different parameters to really see the effect of these different the alpha 1, alpha 2, lambda 1, lambda 2 parameters that we can control. Essentially control the strength of our regularization in a few different things. So they're pretty hard to tune, and so I thought it would be good to actually see it visually represented, and we'll go through that with a very hard regression problem. So anyways, not really too much pre-processing to do today. I dropped the rows that have null values as much as possible, and then one out sex. Okay, with my features, my x values, my y, putting that x and y, putting that grading x and y, and then making a train type split. Okay. So I just wanted to see what I would get from a linear regression here and what I would get from ARD regression. So as we can see here, 24 points and 10 points score R squared for the linear regression, and then the ARD regression does a lot worse on the training score, but does a better on the R squared. And this has to do with the regularization that's built into it. Okay? And essentially is trying to help not overfit to certain columns and stuff, and using lasso and ridge regularization along with some other special tricks. Okay? So if L1 and or sorry, alpha 1 and alpha 2, these control the noise of the target variable. So what that means is it's going to put a lot of emphasis on the relevance of features. If there's no noise, if there's no randomness to this, it's going to have a lot more confidence which features work. If there is noise, then it's going to be a lot more unsure what is working and what is not working. And then we'll put a lot of emphasis on the features that are working. On the coefficients, we'll keep them smaller. Lambda 1 and lambda 2 is a lot more like controlling the lasso and ridge regularization. L1, or sorry, lambda 1 is like L1 lasso regularization is going to try and force as many features to be as small as possible with a couple large ones. So trying to reduce the number of features with usually maintaining a couple larger ones. Lambda 2 is the goal of this is to actually try and reduce the number of regularizations, or sorry, reduce the number of features, or sorry, reduce the number of large features. So really trying to spread out the coefficients across all of the columns, so that not any one of them is very large. And so here we have our alpha 1. Going through this, I'm going to make a range to loop through. So we're going from 1 to the e, so times 10 to the negative 4, places in the decimal places over 4, going up to 1 with the decimal places over 8 decimal places. Okay, creating 28 numbers in between with numpy log space, and we're going to iterate through that. And we'll see here what I'm going to do is I'm going to go iterate through that. I'm going to go alpha 1 is equal to the alpha, and then I'm going to going to fit my model as I train this. So I'm going to train it with a different alpha, fit it as I do that. Initialize my model, I get the score for the train, and append the score to my train score list. Do the same thing for the test, append the test score to the test list that I have here. I'm going to concat the coefficients in here. So notice here, not complicated, but just to walk through this. So I'm putting in the coefficients, my list right here, I'm concating it to my data frame. And I'm putting in a data frame versus a series. And this is so that I can do the dot t. They need to have that second dimension to be able to tilt it. Even so it knows it's one column to get started, so I'm going to tilt it so that it goes in like a row. Okay, so that I can then do my plot right here with the magnitude of the alpha and then the coefficients here, and we can kind of interpret this. So here, and then I'm just going to just one other thing here, I'm going to put the index value to the coefficient data frame that I'm building here equal to rounded to 2 decimal places on the value here, columns equal to the features that we have from up above, making the x data frame before we do the train test. But, okay, so I'm doing here CMAP dark palette, reverse false, and colors 100, kind of making it very close to a continuous color palette. Now what's happening here is we're saying that as the handle length, we have a higher feature, and then we see as we turn the alpha up quite high, we get rid of population, drops off almost completely, and we lots of these are they're very close, but they're really centered around very close around 0. And then you see population Vic. What it's going to do is when we turn the alpha 1 up higher, which is going to encourage a higher degree of feature relevance. So it's going to truthfully encourage them to be a little bit higher. So as we turn that off, it really pushes one of them to a negative value and one to a positive value. So it's encouraging their importance. Right now, these are going to become more important stuff as we turn up the regularization. So it does happen very, very subtly to other features here as well. And this has to do with the scale. So again, just kind of noticing the effect. It's pretty hard to tune all 4 of these together. So to have an understanding of just one by one, we can get a better sense of how to tune these properly. Okay, we might just end up doing with a grid search, but it's helpful to understand what we're doing. So here what we're going to do is we're doing concat. I'm going to do the train scores and the test scores that I was collecting up above. And you can see that once I turn the alpha up to a certain point, my train score gets better. I start overfitting, and then my test score drops. Okay, so at one point it became that we were kind of ignoring our features. We were putting too much relevance on some features when we really shouldn't have been paying that much attention to them. So we start to kind of mess with them. Let's go into that, and then let's go into the alpha 2. So this is going to lead to smaller coefficients. This is not ridge regression. This is basically going to say so it's smaller. So it's not exactly ridge regression, but it is going to encourage it. I feel like it works very in a very similar way. All of the mathematics are different. It's approaching it in a different way. It's going to encourage the same thing that ridge regression does, and smaller coefficients, kind of more spread. Unlike the other one, took a stance. Alpha 1 took more of accomplished a little bit more of what the L1 regularization, lasso regularization is trying to do, but it approached it by emphasizing whether or not there's a lot of noise, a lot of variation in the target, and kind of correcting for that. So it does the same thing, but with different mathematics. And so I think lambda 1 and lambda 2 is good. That works as well like lasso. So again, this alpha 2 works a lot like ridge regression. And what it's going to try to do is it's going to try to push all of the features to be as insignificant as possible here. And you see, even turning it up a little bit, it really does the job. It really kind of pushes these ones to as little as possible very quickly. And you can see here, it really starts to have a negative effect on the score. We can see when it drops off right here is where it starts to have a negative effect on the test scores. It starts to drop the test scores, but not really increasing decreasing the train scores, but then not moving the test scores forward. So decreasing those well in line, and that's not but really see. Okay, so again, kind of having like too much of these is too much, but really there's a very good range where it can work. And often what I would say is maybe start with trying with defaults before we play around with it, and then an often thing is to find out the mix of all of these together. So the grid search would be next. But it's going to be really good to kind of fine tune it and target after we understood what each one was doing. So let's get into lambda 1. And the goal is it's going to instigate degree of sparsity, but really what it's doing is the same thing lasso regularization is trying to do, where we push as many coefficients to 0 and leave the important ones here. This doesn't actually specifically say it's exactly like or using that same form of mathematics, but it really is accomplishing. Again, the alpha 1 is trying to accomplish the same thing as lasso, and lambda trying to accomplish it. They approach it in different ways, but the final result tends to be the same. Okay? And you can see here what this is doing is this is pushing the features to 0 quite quickly. And you can see when we look at our final scores, we get really terrible scores quite quickly. When we turn off the features, it basically pushes it so much that we're basically turning off the importance of all of the features, and it just starts predicting well altogether. We kind of confuse our model to an extreme. Okay. So we look at this one. Let's do the 2 here. So if we run this, and so what alpha 2 is going to do is it's going to do, oops, alpha 2 is going to, actually that's like 2 of them. And what this is going to do is going to do the same thing as ridge. It's going to try where lambda 1 tried to accomplish the same thing as lasso. Now 2 is going to try and accomplish the same thing as ridge. So it's going to push all of them to not be as large as possible, to be as small as possible, and kind of spread it across all of the features. So kind of making it more, we would call it regularized, making sure that not one feature is more important than the other, and allowing it to essentially allowing it not to favor one or the other and be less prone to overfitting. So we went through our same loop here, collecting the coefficients and the scores. And we can see here, we're getting a lot of, it's interesting that the population had so much to do with the age, and some historical reason for this population of penguins. But here we can really see that that population, it tends to be one of the favored ones quite quickly when we spread it around. Although it is trying to spread it across, it is very clearly favoring the population thick and the other population as important features, is increasing one and decreasing the other. We see that effect along the way with all of these other ones, and as it is a very low parameter, we see that the effect is more diverse, more spread across. And as we turn up the regularization to really extreme values, is really forcing it to choose kind of more important ones versus and then looking at the score. And you can see at a certain point, really just starts affecting the score. I think the overall kind of emphasis from all of this, although it's good to understand what each one of these coefficients do, I truly usually, and I still, even after studying exactly, playing around with all of these, I still and as we can see here, the score, it's been more consistent. It seemed like very quickly we really started to push our model to be, I guess, overfitting very quickly. It seems that it would be more advantageous to have kind of a better blend of the L1 with the L2, focusing a little bit more on the last. So we see that worked better. And so we could try and play around with those, focus those on our, maybe our grid search and focus on those. But now we have a sense of how each one of the hyperparameters work in ARDRegression. I honestly, I do use the defaults quite often because they do work really, really well. I play with them a little bit, but they're very sensitive. I think that's the kind of thing we see that the scores fall off very quickly. I mean, our scores were just very bad here from the very beginning, and that is likely the reason that we're seeing such an emphasis. But what we see is that they drop off very quickly. So what I found is actually a really good thing to, when you're playing with these, start with small changes. It's not, you don't need to do a grid search for a big range. You actually need to do it for a fairly small range because, as we've seen, high values for any one of these tend to make the model perform less favorably. So it's kind of like a little bit of regularization is good, but not too much. It's kind of the theme here for turning up all of these features. None of them made it better when they got too strong. So it's kind of, this is really a hard one to tune. So go slow and start with the defaults tricky. Okay? So use those as a baseline. Thank you for joining me, and I will see you next time.